Hello and welcome back. This video we're going to introduce something new that we haven't yet talked about, and physics is very subtle, and understanding these quantities and what they mean when we introduce them is paramount in being able to apply them as we move through looking at different scenarios. So imagine that I have a bag of groceries and I need to walk from here to the other side of the parking lot with this large bag of groceries. And I walk across, and as I'm walking, I'm getting more and more and more tired. I feel like I've done a lot of work by carrying these groceries from the door of the grocery store all the way out to my car in the parking lot. And yet a physicist would tell me I did no work at all. So work must have a very different definition in the physics world or in the real world than it does in mainstream lingo. And it's very common for us to in mainstream lingo to use these words very loosely, but they mean something very specific in physics, and we have to be very careful that we get very comfortable, confident, and familiar with it. So work is going to get the symbol W. And the definition of work is force dotted into displacement. So force is what we're used to seeing force as, F. Displacement, D. Earlier got the symbol delta X in one dimension. So we changed the symbol here. My apologies, it's traditional that we do this when we start introducing work, and you'll see just about every text change the symbol for displacement from delta X to D. So D is our displacement. Now you look at this dot right here and you say to yourself, that just must be a multiplication symbol. And we've somewhere in our math studies maybe used a dot to imply multiplication. But dot product has a very specific definition. It is not the same as just simply multiplying two numbers. So this is known as a dot or scalar product. Dot or scalar product. Anytime you have a dot product or a scalar product, you can find the result in a very standard way. So let's say I have two vectors, A and B, that I'm dotting together. So here is vector A, and here is vector B. And I want to know what is the dot product of vector A to vector B. Well, it's equal to the magnitude of vector A times the magnitude of vector B times the cosine of the angle in between vector A and vector B. So theta is the angle between A and B. So let's put A and B tail to tail so that we can define that vector here. So here is vector A, and now here's vector B. And so this angle theta is the angle as we've defined it in the dot product. So notice that I can take vector B and I can split vector B up into a piece that is along vector A and a piece that is perpendicular to vector A. So vector B can again be split up into a piece that's parallel and a piece that's perpendicular. I'll call that B perpendicular, and I'll call that B parallel. So which is which? Well, this is that angle theta, right? There's my angle theta. And this piece right here is the piece that is, let me just move A over so that I can, let's put vector A out here. This is the piece right here that is B parallel, and this is B perpendicular. Notice that B parallel is going to be equal to the hypotenuse B times the cosine of that angle theta, where B perpendicular is equal to the hypotenuse B times the sine of that angle theta. So if I take this length that is along the direction of A, which is B parallel, B cosine theta, and I multiply it by A itself, then I have exactly AB cosine theta. In other words, this part right here is B parallel. So I'm taking the magnitude of one vector and I'm multiplying it by the magnitude of the other vector that is along the same direction. So I'm taking vector A and multiplying its length by the piece of B that is along A's direction. That is what the dot product is implying. So when we look at work, we see we're taking two vectors of force and displacement, and we're multiplying them in a specific way. That is, we're applying the dot product or the scalar product. So we put in two vectors, but out comes a scalar quantity. So work then is going to be equal to the magnitude of the first vector, which is the force that's acting, times the magnitude of the second vector, which is the displacement, times the cosine of the angle between the force and the displacement. So this can be written in a couple of different ways. We can write this as the work is equal to the force times the part of the displacement that is parallel to the force, or we can write it as work is equal to the displacement times the part of the force that is along the displacement. So here D parallel is displacement along force, and here F parallel is force along displacement. Okay? They're exactly the same. These two quantities are the same. You can look at it either way. You can look at it as the displacement along the force times the force, or you can look at it as the force along the displacement times the displacement. Either one, you're going to get exactly the same answer. So it is also thought of as the projection of one vector on the other. Notice that if I shined a flashlight down so that it is striking vector A perpendicularly, it would cast a shadow of vector B that is B parallel. So the shadow or the projection of vector B onto vector A is B parallel. And that's another way to think about the scalar product or the dot product, is the projection of one vector onto the other times the magnitude of that vector. So let's look at the units we're going to have for work, okay? So the units for work, remember when we put brackets around a quantity, we're just talking about that quantity's units. The units for work are going to be the units for force times the units for displacement. Well, the units for force are newtons, and the units for displacement are meters. And so a Newton meter, in honor of a scientist named Joule, is going to be called a joule. And of course, we aren't going to write it all out. We're just going to abbreviate that capital J. So work is going to have units of joules, abbreviated capital J, and is the projection of the displacement times the force, or the projection of the force along a displacement times that displacement. So using the dot product, new quantity for us, we are able to put in two vectors and out comes a scalar, and it's a very simple application to find the dot product. Again, it's just the magnitude of the first vector, which is the force, times the magnitude of the second vector, which is the displacement, times the cosine of the angle in between the two vectors. So this gives us a little bit of an introduction, and next time we'll move forward from this point.